Good afternoon and welcome everybody. My name's Tommy White. Welcome to this webinar today. I hope you can all hear me. So, what I'm going to do first of all is just going to pop up this little screen and just go over what we're going to talk about. First of all, free software. We have 3 programs that you can use for doing analysis and design of single span beams. And we have a free version of the simple steel beam designer and a free version of the concrete beam designer. And then we have our main frame analysis will also do steel design of single span beams. That's restricted to design, I think, of simple steel beams. We then have our commercial software. Our beam designers now go all the way up to 16 spans in steel, concrete and timber. And then we can also, for those more complex structures, have a frame analysis engine linked in with our beam design, so our steel design and MasterFrame or concrete or timber. The advantage here you'll see is that it doesn't have to be a linear, simply supported or continuous beam. It can be grillages and it can be in manger frames as well. And the smallest version of the MasterFrame is the 50 member. So you can start with a 50 member and as you require, grow and expand the system. We then have something called PowerPad, and to all our students, when I'm talking about PowerPad, I'm talking about your student version of the PowerPad as well. It is no different. So PowerPad comes with the beam designers, but all limited to 3 spans. So 1, 2 or 3 span beam designers, very, very useful. And also comes with either a 15, 100 or a 300 member steel and concrete frame analysis. So those are the programs we're going to be looking at today. What we will not be looking at today when it comes to beams is the composite beams. The composite beams and the slim floor beams, they take a whole 1 hour webinar to cover those, and I will probably cover those at a later date, and there are videos online if you want to view the composite beam design. All our design today will be hopefully to the Euro code. We'll also be able to design and switch between the BS and the Euro code. So let's get back, and I'll just minimize that, and I'll minimize my Chrome, and I have the MasterSeries started, but just for completeness, I don't need that and I don't need that. We will start by starting the MasterSeries. So here's the icon, but let's do it straight through in Windows 10, coming through, and I changed the way my menu works, so I now need to come down again to M for MasterSeries 2015, and then I will come into the main program. Now, there are 3 areas of interest here. One is the program, the other is when we do remote support with clients and if we're having problems, but today it is just this MasterSeries 2015 I want to start. So as we can see, it's coming in with the 3rd of February as the date on the software. It's also licensed to myself, and I'm using a dongle serial number 12184. My license today is actually a PowerPad license. So I have PowerPad Plus with 100 members, and I have portals and 100 members in steel and concrete and beams. So that's all we're going to need today to do this presentation is the PowerPad. It doesn't matter if we're doing the bigger stuff, PowerPad will cover it. Coming into the design, where we want to be is we want to look first of all at the beam designers, the quickest way to design and analyze beams in steel, concrete or timber. So we go into designer suite and we choose either concrete, steel or timber, and I'm going to go into steel. Let's start simple, and we can see we can do 1 span beams, We can do continuous beams. We can do a two-span beam, what I call a cantilever with a backspan, and we obviously can have varying loads, and we can have multitude of subframe type analysis. So I'm going to take a brand new file called demo1 and create new. And I come in by default with this subframe. So this is the default frame that you get from scratch. And what I'm going to do before I do anything else is I'm going to customize this to what I want to use over and over again. Well, I'm happy with the spans, but I do want to make sure to use S355 for my steel and close. I'll then move to my supports and I'll remove the upper columns. There they go. I will set the lower columns to 0, so they've disappeared. And it doesn't actually matter because I'm not taking the columns out, but just for correctness, I will set these also to 355 and close. But I'll change the fixity here to being pinned. And now I've got my traditional simply supported continuous beam. Now, the other thing I want to do is, because I'm using a wide screen, I can afford to have 4 images, 2 and 2 wide, and that's how I want to see any new beam set up. When I come in, take a brand new file, I want to use that. So defaults, I'm going to use this as the default for a new beam. Come back out, say OK, say yes, and let's go in again, back into steel, and I'm going to take a brand new file called demo2, create new. There's no picture because it's not there at the moment, so create the file and you'll see, bang, in I come. S355 set, 3 spans, no columns, very simple. So what have we got? We're in the PowerPad version, so we have 3 spans we can play with, and I'm going to take the second span off and say it's a 6 meter, and I'm going to make it a 1.9 meter. So a short span at the end. I'm going to change my dead load to be 4.8 and my live load to 2.5. But I'm going to tell it to use the spacing here, and I'm going to put the beams at 3.8 meters apart. So it's going to multiply those loads up by the spacing. I'll add in self weight, and since it's steel, I will want a serviceability live load only as well. So what have we got on the screen? We've got our loading, and I might actually pop some values on there. We've got our deflection, we've got our bending moment, with the moment at the support, and the maximum in span, not at this point, but in fact over here at the maximum in span. We then have our shearing force, and of course these shearing forces will help us to look at our reactions. Currently we're looking at all loading cases, and we can also look at all spans loaded or live load only. Now, if we're dealing with BS or Eurocode, we will probably want to have alternate loading, so we get the worst deflections when it's lightly loaded here and heavily loaded here, and the worst sagging moment when it's lightly loaded here and heavily loaded here. So what we now have is all spans loaded, max min and min max, plus our serviceability. Now, the last thing I want to look at before we move on this page is the loading factors. We're currently using the BS factors. I'm going to go into design code and elect to use EC3 and elect to use the Eurocode norms for the UK rather than the Eurocode norms. So I'm going to use the Eurocode with the UK national annex. You can add in your own national annex, it's dead easy. So now I'm working with 1.35 and 1.5. I could, if I wanted to, actually change that to 1.25. And what you'll notice is this is a holy WYSIWYG. What you see is what you get. If you watch the moment 134, I change that to a 3 and it goes back up to 135 and 1.5 for the live load. So it's fully interactive. We can also use all these buttons on the left and the right side to scale up our diagrams, and that's for the point loads, which we haven't done yet. We can separate the diagrams a bit more, and we can even magnify our deflection, so we can see that this span is so high that we're not getting a rise. We're getting a rise rather than a drop in our deflections, and likewise we can move up and down our diagrams. So that's very simple, very straightforward. So now what I'm going to do is I'm going to look at some of the intricacies of this program. So we've set our spans. We want to come into supports, and the first thing I can do, because I'm not putting any supports top and bottom, is I can add a cantilever. So I tell it that the last span is now cantilevered, so now that's lifting up. That's why we were getting no moment lift up beforehand. It wasn't a cantilever. And you can see instantaneously the effect of the lovely curvature here, and suddenly release it, ping, off it goes. Naturally, if you did the opposite, that could be quite problematic as everything goes walkabout. So put on the cantilever here and we'll now see the effect. We can now come along to the third tab and we can put on our additional loading. We've got our blanket load, and if I come back actually to that, I apologize, every time I put a value in here, if I don't change it, it's the same. So if I wanted a lighter load on the balcony, I could say that the balcony has 1.5 kilonewtons of a live load, not 1, but that will still be the 4.8. Coming back to my point loads, and I'm going to put a point load at the end of this span, which is in span 2. So I can either say span 2 and has a dead load of 15 on 1.9, so there it is, and it has an effect. Or I can do a different tack and say no, I'm not interested in which span it is. I want to put an additional point load of 12 kilonewtons at 7.5, so slightly closer in, but I'm referencing this one from the origin. And the nice thing about that for these point loads and these patch loads is that we can then play around and move them on the screen. We have these little spin buttons where we can actually touch the left and right of this label, and it will move the load to the left or the right. Now, the increment at the minute is 0.1 meter, that's fine, which means I can take these and start to move them. Now I can't get that one past the end of its member because it is stuck on member 2. But this one is referenced from the origin and I can move it anywhere I want. So if we wanted to place this load at the position that will give us the minimum overall displacement on our left beam, I'm seeing it's going to be, well, probably there, around there. It's going to give us the lightest deflection. So we have this ability to move loads about on the fly and see the effect. We can also do it on all of the point loads and move them both at the same time and see what would happen. And that's fantastic from a visualization of how structural mechanics works, but it's also great for locating objects on remedial work or upgrading existing members to put on crane loads or whatever. You can position them to get the least out of the deflections, or least bending on your frame. Naturally, we also have these partial loads, and I can say that on span, again, 0, I'm going to have a 10 kilonewton partial load, and it's going to be no live, and it's going to start at 2 meters out. Well, it's going from 2 to 0 at the minute, and it's going to go to 6, 7 meters. So it's going to run from here to here, where it catches up the slightly lighter live load, so therefore the total is different. And again, I can move that about because it's referenced from span 0. And finally, I can also add in a varying load. So to make my life a wee bit clearer for you to see, I'm going to take those two off, so those are no longer applied to the member. Go back to my varying load, 0. I'm going to start at 2 meters. We're going to end at 6, and we're going to have it as a dead load of 12 all the way down to 4. So it's adding on here from 12 down to 4. And as I now move this 100 mil at a time, I can see it moving into the next span again dynamically. Now, the quick and smart of you will have spotted, because this is a 2-span beam and we're doing envelopes, loading here has to be maximum when this is minimum, and vice versa. Well, when we do our loads this way, we don't have to worry. It looks after it all for you. There's no worrying about whether it's a D1 or a D0 or a D2 load. All of that is done internally in the program. So we'll leave this horrendous little bit of loading and horrendous deflection, and we're going to try and design it to get our deflection down to, I'm going to say I want a maximum deflection for surface cases of, well, actually, because it's quite high in the ultimate cases, I'm going to say I want it to be a minimum or a maximum of, say, 10 mil. So what I can do is I can now go and design this beam. But before I do that, there's one more trick up my sleeve in this, and that is the fact that I can have it set as one section, so both beams are the same section. Makes sense in this case. But also, I can add an additional beam. So I can put in beam 2 with no additional load. And I come here and take that out. So that's very flat. So it's the same beam. So I've got now 2 beams in my collection. Design, steel design. Very simply, in we come with that trial section we put on, the 457, 152, 67. And we'll see that my deflection case is giving me a deflection of 2.2 mil. And I will see that it's giving me we'll see we're designing the Eurocode, and it's class 1. We've got a very low shear, and we've got a moment capacity of 0.3. So if we're not happy, if we're not got a problem with deflections, we could reduce this beam size right down. So if we work with these deflections that we've got here, we can come along and say, take this beam and come down to 406, 356, coming down again, just down through the list, 254. So the shallowest section that's going to work is the 254 by 37. Now I can then sort this by weight order instead, and I can just walk up and see if there is a deeper section that was lighter that would work. In this case there was. But I don't even have to do those manually. I can use the lightning bolts. So lightning means automatic. So up it goes and it reassigns the section, and it finds me the lightest section. Move to the second span, and this is not happy with deflection. So it's going to govern, because the 2 sections have been told always to be the same section. And if I auto design that, it's coming back up to 406 by 39, and that's a pretty deep beam, give me the best deflection without putting a weight up order. So if I can work with the heavier weight, sorry, the deeper section, I'm happy at the only 39 kilograms. If I have to work to the shallowest, I would have to go to a 305, would have to be a 54. So we have this flexibility in the design, and as you will see, that then works here. So what have we been designing? Very, very simply, we have been designing the full length of the beam fully restrained. So we have said it is fully restrained. So let's assume that this beam is no longer restrained. We can say it's not fully restrained, but it's the standard 1L. And we'll see that this section works because it's the other section that was the problem. So moving over to the other section, if we say it's not fully restrained, but 1L, we'll see also that the deflection and everything else was controlling the size of the section. So now we can see that we're still okay. If we go one stage further and say, well, this is actually a cantilever, so a cantilever with end free, and we would probably decide to come here, if it's pretty free, to at least 1.5L on the cantilever end. That's still not giving me a problem with the section size that I've chosen. Somebody actually asked, what do we do if we have a member that is sort of restrained at one end and free at the other, so restrained here and free? Well, what you can do is you can come along and you can say that end 1 is 0.1, end 2 is 0.7, because you can say it's cast in, and then it uses the average of the two. So you can stipulate different end conditions for the two ends of the member. If we want, we can then introduce instead intermediate restraints. So if we had joists or purlins or whatever along this member, the alternative is to come along and say we work with 1L, which is normally as per end 1, to keep it simple, and then we say, but we have restraints at 1.5 and 1.8 and 2 meters. So we should find in here, when we move over, that we're checking it at the lateral positions. So that's your beam design, but we also have this little hugging moment. So what we need to check, and if we just click on the member, is we have this here, which is a check to Appendix BB in the Eurocode. It was Appendix G in the old BS. And we'll see that that's fine on restrained, and obviously the unrestrained portion up here is also quite critical if we have no restraint on the top flange, and we'll see again that this works. Now, having done all that, it's probably prudent to resize or to reanalyze, and then to recheck everything is fine by clicking on the members. Now, there are some additional buttons here, and this one would size all the visible members the same section size, which is not necessary here because it's only little beams, and likewise that would do a lot of members, but the one section size. And this is not that relevant in here at all. This is the one you saw that says Reanalyze, and this would scan all the members and stop if it found any of them failing. So if it found any of the 2 or 3 or 4 or 6 spans that were failing, it would stop at that to help allow you to go in and design that. So that's your simple steel design. And remember, I had 2 checks. So that was the first one. So that's the second one, because that was the one we were looking at with no additional load. I'm now going, excuse me, to, excuse me 1 second. To the same design but with the additional load applied. That's the brief analysis brief 1, and we'll see that both of these still work. Well, actually, because we haven't resized this one. So if we resize this one and resize both sides of the member, it's done it all for shallowest, and it's come up with the same 54 kilogram section that seems to work quite well. In this case, the 54 is right on the money in terms of in span moment. We can see our moment capacity is so close, but bear in mind it will assume by default on this one that's fully restrained. We're not going fully restrained, we're going back up to 1L. It's now failing, whereas the other member with the lighter load didn't. Back to auto design, resize again, and we'll now find that that is now requiring a 406 by 85. To keep it the shallowest, by weight order, we could have got around with actually something, sorry, a lot lighter, and it's just over there, and so we're very close, and it's just asking me to intervene because it's so close it wants me to have a wee quick look at it, but we can see now it does work. So that's your simple steel beam design. Now I've taken a lot of time over this because this is the core for everything that we're going to see. And I'm just going to exit and say yes. And now I'm going to do a concrete beam using the concrete beam designer. And we'll just take something similar. I'm going to take this one and say get new. And it looks identical. Well, not quite identical. We've got our spans as before, but we've now got dimensions rather than a section size. So we've got a rectangular section that's 1 meter wide, 200 deep. I would call that a slab. I'm going to turn this around and call it a 300 wide by 550 deep rectangular sections. We have T's, L's, R's, and super members, which we will talk about later. And I'm going to put a dead of 4 and a live of 5, add in self weight, and put a spacing again of about 3.9. And we don't normally consider the serviceability deflection because it's done separately in the concrete. So supports, we don't have any, thank goodness. Point loads, we don't have any. Variable loads, we have none. So we can still do all of those things. We can go to varying loads, point loads, but that is just a repetition. But what I haven't shown you before is, remember when I could move my point loads back and forwards? Oh, there's some point loads. Let's keep those on for the fun of it. But I think I might reduce them down to about 7.5 kilonewtons. So they're a wee bit of an effect. And I'll give them a 10 kilonewton live at the same time, for whatever reason. But as well as moving these loads about, what I can also do is I can move internal supports about. So I can't move the end and I can't move the free end, but I could move an internal support. Now in this case, the increment is down to 1 millimeter at a time, which I think is a wee bit difficult to control. If I make that 25, then I can increase the increment to 1.1, and then I can start moving supports about. So it was around about 1.8 cantilever, so I'm going to leave it at 1.825. I can naturally come in and re-edit these if I wanted to make them 6 and 1.8, but I'll just leave it like that. And again, we can see our loading combinations and loading patterns coming through. Now, design. Very similar, but we go into concrete design this time. I'm going to kill the concrete design because it's a bit more complicated. I'm going to start from scratch with this 2-span beam, and I will see I've got a beam with some reinforcement. I've got some sort of diagram. Obviously the top bit is the reinforcement in the beam. B16s, B16s, B20s, B20s. This here is not a bending moment diagram, but a force diagram, because we're in euro codes. It's the measure of the FT in the bars, and it's 1400 newtons or kilonewtons. I'm not sure which, but it's 1400 with a applied of 1076. So we can see we've got some reserve here. We also have what I would have expected, this blue line plus this flattening of it, and also this flattening up here. And what those are is something called shear drag. In the euro code, the shear reinforcement, or the shearing on the beams, applies an additional drag on the tensile steel because of the truss action of your analysis using a truss model. But it does quite kindly say it can never be greater than the maximum, so that's why we get this capping off and not an increase in drag there, and likewise here. And then the red is the capacity. And unlike the BS, the Eurocode allows you to taper off the capacity of the bar as it gets closer to its anchorage. So we'll see as bars overlap, the lap length is longer than the anchorage, so therefore you do get an increase. If the lap and anchorage were the same, this would just be constant for the same bars. So we can see our bars, and I'm just going to come along and drop this down using left and right mouse buttons to be 25s, and I'm going to see that I could get away with 430s, which will fit even though we've got a 3-link arrangement. What about 525s? 525s on the money, nice sweet spot positioning. I would then take this and reduce that down to 4 and possibly pull that down to 16s or 20s. And likewise at the bottom here, I would curtail that down. So we're now coming in nice and neat in with 4/16s lapping in. And on the top we've got 3s and 4s. I don't like that. I prefer to use the 5 bars in the middle, and then we just lap it with 4s in the ends, because we don't need that extra bar around there. And we can see our links. Now, that's our bending moment and our tensile forces. We also have, and if I just double click, our shearing line. Okay. When we move to links, we can see that we have applied no shear enhancement. We can use the shear enhancement up to the column edge, and we can then use the enhancement to a column edge plus an effective depth. So those are the old-fashioned rules that are in the BS and also in the Eurocode. So we're taking it and we're curtailing it up to there. That's great. In this case we don't need to, actually, because it's well in with that third leg on the breadth of the section. We possibly could have got away with the 300 being less than 3 links. So I'm actually going to reduce that down. Well, it's not important because it's not been applied. If I come to the nominal and I come down, you will see that if I had 2 legs, I'm going to have a failure here. So what do I do? Put the extra leg in, or add in at the support some additional reinforcement at a heavier pitch, and I'm going to put in the number of sets. So this is where I'm going to add them in. In they come, they're starting to come out, and there we've now covered with this wider area the number of this higher shear region. We also have in the Euro code this great reduction in shear that we can apply, which is like a dragged shear reduction, and it can get quite hairy because it's doing a curved reduction in shear. And can I use that with no additional reinforcement? Again, it in this case would still require those additional bars, and type that in. So that's the concrete design. You can then move across and look at the cantilever span, and you can see that 4/16s, and we would just make that 4 to make it proper, will link in together and everything's happy. And we are seeing a little blue line here, and that is telling me that something is not happy. And if I click, we will see that it's an ever so tiny overstressing, but that's not what it was annoyed about. It was annoyed about the width of laps, and the maximum link pitch can't be greater than 40 because of the size of the compression steel. So we have a few things that we really should sort out, and one of the ways to do that is with laps, is if we put in a slightly wider section. So let's go, and we'll come back to my beam data, and I'm going to change it from 300 say to 350. That's going to give me more room. That might let me get away with using 4 bars instead of 5. No, not yet. So I'm going to put in, and maybe put in some additional compression steel. So if I stick with 4s here, here, and here, we're still not getting it. So we need to think about either increasing the depth until we make it work. So 700 would work at say 350. If we were to go up to 400, we would get away with still 700 wide. So 700 with 350, 700 with 400 is going to give me the same answer. We might as well stay with the slightly narrower, and would we get away with 300? Just, but it is problematic with the lapping of the reinforcement. So I now only have a problem when I come to my laps, I think, and if I look at my results, everything looks good except for the bottom laps. These are 180 millibar, and I can only allow 140. So one thing I could do is I could lift these bars up, or I could crank the bottom bars. So taking that down to 16 is going to help, but it's not going to solve it. I can then say, let's just move that into a higher layer, take that one and move it up into the upper layer, and now because they're sitting above each other, it's not problematic, and we will see then that these bars are sitting over the top of each other and not touching each other. So that's one way of solving that problem. So as you can see, we have quite a flexible arrangement of playing around with the software. Now, if you want more guidance on concrete, there's a fantastic webinar on concrete design. So coming back out, I've covered 2 programs. And coming back out, you'll be glad to know that the 3rd program in this harmonious suite, the timber design, is virtually no different. So let's just take an example you've done before, and we can see you've got 2 spans of 4 meters, and it's continuous. Otherwise you would have just done one. No additional loads. It's, at this case, I think I should work not to the BS because that's serviceability, to the Euro code. Yes, please. And we now have 1.35s. That sounds good to me. and some nice deflections, and I'm not going to go for any more other than the section is going to be, and it's a pretty big section it's put in because it's putting it in as a timber section. I don't know what I need, so I'll just leave that as it is at the moment. We're carrying 1 meter wide of this loading, so we shouldn't need anything as big as that. So into design, timber design, and we'll see that I'm absolutely correct. Our designs are well under. So where's my materials? Let's make this into a 75 wide. So the bearing is a bit of a problem at 75 wide, and possibly looking at the stresses would help that. And 550 deep, I'm going to go for 220. So 75 by 220, so the bearing was being reduced down by the length of the aspect ratio. So a 75 by 220, which exists in, I prefer something like a C20, is going to work. Now, we are refactoring this program at the moment for our 2016 release. There's going to be some nice new changes, and one of those is the ability to actually have your own section properties as well as the standard ones for the glue lam and the BS designation. So if you're using European timbers that aren't standard, you can actually put them in, or American or overseas timbers. In our case, we're doing this for internal use, continuously heated building, and I'm looking at the moment at seeing this not having any problems whatsoever. So the design brief is actually with moment, material specification, as we saw. If we wanted to, we could do them glue lam, but I don't see the need. It is carrying a 1 meter width of loading, which is more than you would expect on an 8-inch joist. So it is expecting something a lot deeper. So I am going to come back out of that and go on to the other way of doing it, because I said we have an additional set of programs. If you remember, we've only just looked at the beam designers, be it either the free or these. We've got these little babies here to look at, and we're just going to, in the last 5 minutes, do a review of what is in these programs. So if I go to MasterFrame, into MasterFrame, this is a program that will do colossal buildings. This is a program that will do very adventurous buildings. This is a program that will do very extensive multi-story frames. But this is also a program that will do my wee beam, and I create new. So either a continuous or a simple beam. And if I just say, let's have a simple beam, straightforward, we'll go for a steel section, S355, and it doesn't really matter what it is. I am going to ask it to be a length. So I need to come out of here and I need to edit my coordinates. So change the 9 meters to, in my case, 6.6 meters. And now let's look at the loads. So member loading, let's put some loading onto this member. 2 UDLs and 2 point loads. So a dead and a live. Because we're in MasterFrame, it's far more flexible, but with that comes responsibility and the fact we need to understand what we're doing. So we're going to put a 12 kilonewton per meter run dead load, and I'm going to put a live load of 15, and then I'm going to put a point load of 5 and 5 and I put those at 2 and 5 meters. So what do I see? I've got this little frame, single span beam. It's got a pin and a roller, a couple of point loads, and we'll just push that so it's actually on the member with the arrowheads. That looks better. And obviously in my case, my distributed loads need to be a bit bigger. Put some values on. There we go. So we now need to look at our loading cases. So loads, loading cases. And luckily for us, with the 2015 version of the software, we have the ability to automatically create cases. So I don't need any dead and live and wind. It's dead and live only. And I'm just going to ask it to replace all of them and generate the loading cases. And I now have my standard 8 cases. Oh, I asked for sway stability as well. Not to worry, that's quite interesting. I'm just going to go back in 1 second and say I don't need equivalent horizontal forces. Otherwise, I'm going to end up with a lot more cases than I would really like. 4 cases. The 2 different variations of the Eurocode Dead and Live Ultimate, plus the serviceability all loaded and the serviceability. And I'm just going to go in and analyze and do it as a plane frame and design, steel design, and it's no different from this point on. It's exactly the same as you would have in the beam designers, and likewise for the concrete and the timber. But let's step back, because if we're talking about beams, we can also talk about, particularly when we come to concrete, your little subframes. 50 member frame analysis might cover that. I don't know, 1, 2, 3, 4, 6, 7, 8, 9, 10, 20. Well, 50 should be covered. I'm looking for a little set of ground beams. A little small domestic ground beam arrangement, or a more complicated. Let's go for the domestic ground beams. So what have we got? We have got supports here, 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 and here. So we're looking at beams that are balancing and cantilevering on our piles. We've done this intentionally to make it more complicated, but it is an actual example. We've just taken out 1 or 2 of the piles to show you what it can do. So it's a little ground beam arrangement, and it's loading all the way around, applied onto all the different members, and the design. So analyze this. It's got 2 loading cases. I'm not going to worry about the fact it's not got the alternate patterns at this moment in time. I'll just go into my griddage. So obviously we need something like PowerPad or a 50 member frame analysis to do this. And design, and in this case concrete. And what we'll see is the simple design of the simple beams. We'll also see from time to time that we will have torsional design coming through. So we are going to have torsion in our beams when required, and not when we don't want them, because we can have these ends coming in pinned at the ends so we don't develop torsion around the corners. So very flexible, very, very simple design of grillages of concrete beams. And of course we're looking at the nice pretty diagrams, but we can at any stage look at the results. So we can see the bending, the shear and the deflections, and again it's just a continuity check that has failed because we haven't done the full design on this yet. Now, a little trick for you, obviously, because you're going to want to know how I've done this, is how to set all these little pins. Well, provided you don't have a horrible cantilever that's not got what I call a backspan, so these cantilevers all have backspans, then it's a very simple process. You do not have to come in and do what I've done here and put all these pins in. So if I go to edit and I go to restraints, member end releases, and I'm going to remove them all, so they all go, because it's quite a bit of work to figure out which ones I put in and which ones I don't. Remove them all. We have an option here to ignore torsion. We can also include shear deflection. In deep beams quite useful, in timber quite useful. We're not going to worry about P delta and this sort of thing. So we've already got ignore torsion, so we didn't need those pins. Reanalyze again as a grillage. And when we look at our graphics, so we see them all, and just scale this down, you'll see that it automatically pins at the corners as you would expect, so it's not going to throw torsion all around the place on your system. So fantastic little program. So what's the difference between the programs? Well, I created a wee table here, and very simply, and I'll send everybody who's logged in a copy of this table. Simply supported beams, you can use any of them. Simple cantilevers, you can use the free versions. Partially fixed and fully fixed, yep, they can all do it. And uniform and point loads, yes. When we want to do a cantilever with a back beam, obviously we have to have a commercial version because the free versions are single span. If we want to play around with our own loading cases, we're then going to need to not use the beam designers but the MasterFrame versions. MasterFrame, axial loads, minor axis moments, spring supports and settlements, I never even talked about that. Grillages we saw, and torsion design in steel and concrete. They all will check deflections for you, and the shear deflections in the beam designer, it'll do a shear deflection addition for you for timber, but in the MasterFrame, the commercial version, you're able to turn on shear deflection for all of the section sizes, and they all will design the BS and the Euro code. So it's a very flexible system. So now that's my webinar presented. I want to just now look at the questions that have come through and see if there's any that I need to really look at and go through with you. Can we include composite steel? Keith, sorry, it is not covering composite today. Cellular, if we were using the composite design program, we could do discrete openings. And I'm just going to go for new file, take a new file, and steel section. But if we're using the MasterFrame version, either in PowerPad or in anything else, then we have the option for going, and let's just turn on our 3D. There's my beam, and we will make it in simple terms a 533 by 82 kilograms, 533, 210, 82. And that's what it says. If I want, I can now make it into a castellated member, and when I refresh, it'll put the holes in them. So it's going for a castellation at a spacing of 1.25 depths and a hole size of 0.6, and it will allow that, and it's now taken that and shoved it up to being a 608 deep castellated or cell form beam, and we can design that in our steel design. If we wanted to do a beam that had holes in it but didn't want it to grow in depth, we need to use a plate girder, and plate girders are basically built up sections. So I could say I was originally using a 533, and that will never change in depth. It will remain the 533, and it was by 210. And I can set the other parameters to be the parameters of the section. So once we're in built-up sections, they remain the same size. For rolled sections, it cuts and grows. So you have that great flexibility in the program. You also can use the plate girders, obviously without putting holes in them. I never even talked about putting on in the master frame. We can have concrete casing to enhance your radius of gyration in your beams. I never even talked about having a beam in 3D that's got a secondary beam. Let's go for a 12mm plate that is, sorry, 400 wide on top. So there it is, 400 by 12. I'm going to take that off and I'm going to put that in as 400. No, not 4 meters, 400. And we're going to go, what's the thickness? Make that one 400. It's going to look funny. It's a cube. And make this into 10mm on bottom. We can also apply a secondary section. So we could apply a secondary U beam to the side. We can apply a secondary and put it on the other side. We can apply a secondary channel on top. Won't make a difference if it's on the bottom, it'll analyze the same. So we can do all of that as well. Is the module able to do torsion? Well, as I said earlier, torsion is only available inside the frame versions of these programs. So even the simple single span master frame is available. What is spacing? Oh, great prop question. Spacing is not really to do with master frame, it's to do with our beam designers. So you've got a beam to design in steel and you're designing it for a floor. Oh, and somebody actually came and gave us all these different types of examples. Where's my simply support? There we are. And you know that per meter square your dead load is 0.75, and you know your live load is 2.5 meter per meter squared, not per meter run. You can then use the spacing either here or here to magnify that up. So watch the value 4.7. Let's just go for example live load only, and will not add in self weight at the moment. So 2.5 is what we're getting, live load only. If I now tell it that the spacing is 4 meters, that goes up to 10 because it magnifies it up. But I could say in this case the spacing was 3 meters here, and then you wouldn't bother with that. This one overrides all the other spacings, but you could have a different spacing for each different types of load. And as a way of you not having to compute what if the spacing was 3.125 meters, you wouldn't have to compute all your loads up by that spacing. So that's very useful. With timber, can you take in wet conditions? I don't believe you can take in wet, but certainly you can take in the exposure of the timber. If you're in any of the timber designers, you will see that, take this silly beam of mine, and you will see that we're just defining the basics in here, but when we go to design the actual timber design, you will have the material specification, and it is service class, internal, covered, or external. I do not know whether or not external considers it to be permanently saturated. I would have thought so, but I don't know whether that would consider submerged. But certainly wet conditions is for external use. Yeah. You know, unheated covered is a wee slightly damp, whereas that is, I think, wet. So I think the bottom answer is yes, it can cover it. Somebody was asking, is it part of what we're doing part of the student version? Yes, every single thing I have done here is included in that student version. That's basically everything covered. Now, if you want a trial, we're happy to give you trials of the software. You can just log on and I'll just restart my Chrome. So you come into the home page, and if you want to try something big, you can just say let's try and fill in your details and then what you want to try. If you're after, say for example, just the simple steel beam designers, you'd probably just go to steel into the free beam designer or the commercial version, doesn't really matter, and you would request a trial. They will give you the same product, just one will be more flexible for the first 30 days. If you're a student, very simply under the product range, you're after the light suite. 30-day trial, and off it goes. Fill in your details and you're immediately downloading and installing the software. Very, very straightforward. So you're all welcome to try any of our software for 30 days free. You're all welcome to take the simple steel beam designer, that's free as well, and as students you can take in that student version. Now I will give you all one word of caution. The student version is not compatible with the commercial version. So don't think you can take a student version, do the calcs, and then print them out with a commercial version. It will not work. It will not load. And the student version will have all over it that it is a student version, which we're happy for students to use all over the world. So it only goes for me to say thank you very, very much for coming along today, and that we will be putting this on the web in the normal position where you can log in and view the webinar if you so desire. So you can go in and you can go to videos, where we have a multitude of videos, and you will see all of the videos, including the webinars. We also have technical notes, and in fact there are one or two quite good technical notes on the details of using the beam designers. I will provide links to those in my thank you email that I eventually send out. And finally, I think that's it. Oh yes, one last thing. Also, we have a YouTube channel where you can view some of the better of these webinars. So if you want to look at PowerPad in its whole, there you are, with some very detailed output. Obviously we can see retaining walls, floor vibration, everything is all in here. So ladies and gentlemen, I am going to freeze the frame here and say thank you all very, very much for attending, and you have a good morning, good evening, on good night, depending where you are in the country. For those who got up early, thank you, and for those who stayed up late, thank you again. You take care.